In this video, we'll talk about the conversion formulas for getting between polar and rectangular coordinates. So we saw the basic idea of how to set up polar coordinates and how to get from one to the other. Let's try to make that more explicit here. So the point we had was that you would eventually build this triangle, assuming we're in the first quadrant, where you know you have x and y as your two legs of the triangle. Your angle here is theta and the hypotenuse is r. This means I can pretty easily write formulas for getting back and forth between these two systems. If I'm going from polar to rectangular, I can write x as r cosine of theta, and I can write y as r sine of theta, just based on the fact that these ratios work for the right triangle trig here. If we're going the other way, we see that the radius of the hypotenuse, so that's just square root of x squared plus y squared. And for theta, we're going to need inverse trig involved here, because I need to get theta out of this triangle. I can get that as the inverse tangent of y over x. Now that works for first quadrant points, and everything but the last equation works for no matter what quadrant we're in. For theta, you gotta be a little more careful to make sure you land in the right quadrant. What do we mean by that? Well, the thing we mean there is, let's look at two different points. Let's look at rectangular points, 1, 1, and minus 1, minus 1. So if you convert these to polar, for both cases you get that r equals root 2. That's not too difficult to see. And theta should be the inverse tangent of either 1 over 1 or inverse tangent of minus 1 over minus 1. But these are both inverse tangent of 1, which, based on the range of inverse tangent, is pi over 4. However, these 2 points are not the same point, right? If I look at a graph, 1, 1 is up here, and minus 1 is down here. So this one does in fact have an angle of pi over 4. What about the other one? Turns out the other one goes the exact opposite direction. So to get that angle, I have to go around to pi, and then plus pi over 4. So this actually is 5 pi over 4 to give me that angle down there. So because inverse tangent only gives you angles between minus pi over 2 and pi over 2, if the angle you want is bigger than pi over 2, you're going to have to make sure you land in the right quadrant by shifting your angle here. And it's going to be shifting by a multiple of pi. So you're going to add pi to get to the other side to get the thing you should get for the actual angle there if you don't end up in the right quadrant. When you do inverse tangent, you'll land either in quadrant 1 or quadrant 4. If you need to get to quadrant 2 or 3, or you want to convert the quadrant 4 to a positive angle, you'll have to add pi or 2 pi to get there. And you'll see a couple of examples of things going forward. So in general, we allow r and theta to be any real numbers, not within a certain range. But that means that for a given point, there are many different ways you can write it in polar coordinates. Let's go back to our point 1, 1 from before. We saw in the example before, this is root 2 and pi over 4 in polar coordinates. But how else could I write this point? Well, if I go just 2 pi further, say root 2 and then 9 pi over 4, that gets me the same point. Why does it do that? Well, if I look at my graph, the point 1, 1 is up here. I could go angle pi over 4. That's great. I could also go angle 9 pi over 4, which means I'm going all the way around once and then up to that point. That also lands me at the same point on the plane with a different value of theta. I could also do something like root 2 and then negative 7 pi over 4. What does that do? That says start here and go this way around the circle to get to the same angle again. I can also take negative radii. So I could do something like negative square root of 2 and 5 pi over 4. That says go all the way around to this angle down here, and now go in the negative direction, root 2 units, saying go back this way to get to the point 1, 1 again. There's many different ways to write a point in polar coordinates. If you want to get unique determination, which generally you want to do, you can make sure that r is always strictly positive, and theta is between 0 and 2 pi. If you do that, there's only one way to write every point in the plane. However, this means there's no way to write the origin. However, the origin is kind of a weird point in polar coordinates because If r is 0, any angle theta gives you the origin, so you can't really define that uniquely, so we kind of ignore that. But if you want unique determination of points, you want r bigger than 0 and theta between 0 and 2 pi. One more step in this process, let's think about the different coordinate systems and what it looks like when I freeze one variable and the other one vary. So for Cartesian coordinates, if I fix the value of x and let y vary, what I get are x equals 1. I get a vertical line like this. So for fixing x, I will always get a vertical line here. Similarly, if I fix y, this is the line y equals 2, y equals 3. These are all horizontal lines. And now based on this picture, you can see why we call this rectangular coordinates, because every little box here is a rectangle. And it's really easy to write equations for rectangular shapes in this system. What does this look like for polar coordinates? For polar coordinates, we need to think about fixing r and fixing theta. Let's fix r first. Now, r is the distance of the point from the origin. So if I fix r, I'm getting all points that are a certain distance from the origin. So I'm getting concentric circles around the origin. What about fixing theta? Well, if I fix theta, then I'm fixing the angle I make with the positive x-axis, which means I will get rays coming out of the origin for my fixed theta. And then to recognize here, these things are no longer rectangles. They're little weird shaped circle sectors. And that's why we go and talk about polar coordinates, because pole indicates some sort of circular symmetry around it, and that's what you get from this picture, is some sort of circular wedges that are coming out of this shape. So it's important to keep this in mind when you're trying to envision polar functions or envision things in polar coordinates. This is what your grid looks like. It's this sort of a grid as opposed to the actual grid we had above for rectangular coordinates. And this difference here is helpful when we're trying to actually deal with functions that are benefiting by using polar coordinates. As an example of stuff we've been doing, let's find a polar representation for the point 1, minus 3, and at least 3 different ways to represent this point. So let's just do a standard one first. If we're at 1, comma, minus 3, that has x coordinate 1, y coordinate minus 3, it means we're down here. Well, so in this case, I have r down here, and theta comes all the way around this way. Let's see what I get if I plug into my equations. So for r, we get square root of 1 squared plus 3 squared, which is square root of 10. And theta should be the inverse tangent of y over x. And this is not a special angle, so I have no way of figuring this out, but it's going to be some angle between minus pi over 2 and 0. So then how can I get other ways for this point? Well, I know I can write the point as root 10 and tan inverse of minus 3. I could also write this as, say, root 10 and then tan inverse of minus 3 plus 2 pi. That'll be the one that's actually in between 0 and 2 pi, but it's another way to write the same point. I can also do something like negative root 10 and then tangent inverse of negative 3 plus pi. That'll swing to the other side and then go negative direction back. So this gives me 3 different ways for the same point. If I had to pick one, I would pick this one here, because this will have a positive angle in the theta spot between 0 and 2 pi. That's the ideas of polar coordinates and how you can use these formulas to go directly between the different coordinate systems, as well as how they look and how you should think about them when you're trying to visualize what things look like in polar coordinates.